Hello, thank you, Sarah. Good morning, everybody, and thank you for having me. Can everyone hear me all right? I'm Marcee Meinhardt. I'm an undergraduate in the Fish, Wildlife, and Conservation Biology program at Colorado State University. My mentor is Dr. Stephen Fosnot. Today, I'd like to discuss the research and data analysis I've conducted over historic fresh snow density trends here in Fort Collins, Colorado. So measuring snow depth is easy. When it's the dead of winter and you hear, we're getting 4 to 6 inches tonight, you might think, oh geez, I need to get up early and shovel my sidewalk. But how early? How much work do you have cut out for you, really? Is the snow light and fluffy, or is it dense and heavy? What's the snow water equivalent, or SWE? This is the water content and a certain depth of snow. Historically, depth to SWE ratio is assumed to be 10 to 1, or a density of 100 kilograms per cubic meter. But how much SWE is in fresh snow? I had 3 research objectives. 1, explore correlation between air temperature and fresh snow density. The idea that as temperature decreases from about 0 degrees Celsius to much less than that the fresh snow density composition will change and likely decrease as well. 2, utilize 100 years of local daily meteorological data, or MET data, to evaluate this correlation. And 3rd, to compare some fresh snow data collection from this current winter, 2019-2020, to the local historic data trends. This figure is from research conducted by Fosnot and Solis from 2002. They found a general decrease in fresh snow density as temperature decreased. However, there's a lot of variability in the data, even when the data is collected from a similar location. My research is based out of Fort Collins. This is located in northern Colorado at about 5,000 feet in elevation. It's the home of Colorado State University and our local MET station that's been operating since 1889. The historic data was analyzed mostly by utilizing Excel. I first collected over 125 years worth of local daily MET data from National Centers for Environmental Information of NOAA. I received this massive Excel file of almost 50,000 rows. So I had to take this giant Excel file and reduce it by eliminating weather variables that were not of interest to me. I left things like temperature, precipitation, and snowfall. I then did a little more data quality control and removed some other unreliable data, say from 1889 to 1905. Once the raw data was all reduced, I started calculating it into something meaningful. I found daily temperature averages per every single day of the year. I extracted days only that had snowfall. I calculated SWE using precipitation measurements because SWE isn't directly recorded at the MET station. Then I found density, which is a simple equation of SWE over depth of snow recorded. To compare this year's snow density to historic data trends, we did fresh snow data collection after 3 separate snow events during the 2019-2020 winter. These were in October, December, and April. We recorded air temperature and measured depth and SWE by using a fresh snow sampler. This equipment measures these variables directly by using volume and weight of the fresh snow. In summary, these results ended up with 2,390 different snowfall observations over the 100-year historic period that we have on record. We were mostly interested in the air temperature during snowfall events, which varied daily but also followed monthly trends. We were also interested in fresh snow density over the winter as a whole, which we found to be about 10% of observations followed the classic 10-to-1 ratio. Here are some of my results. So this is the average air temperature, flat line being 0 degrees Celsius, and we're following a timeline of the different months of the winter. So overall, the temperatures vary daily, but in general, it decreases through mid-January, and then the temperature begins increasing after mid-January. Fresh snow density over the winter as a whole follows the same pattern as the temperature trend, but the 10-to-1 ratio is evident all winter long here. Here are the average monthly densities, showing the different amounts of observations that we had and their average density over the month. About 10% of all of these have the 10-to-1 ratio, as you can see here. There's a general decrease in density that follows the temperature trend, which is what has been recorded in the past literature from Fosnot in 2002. Here you can see a change in temperature that ranges on average per month of the year. Then this is the results of the density, the average density and average temperature that you can see. You can see how lower temperatures are correlating with lower densities. This polynomial has an R² of 0.39 and a significant p-value of 1.76 times 10 to the negative 14. Very excited about that. And then last, I stuck on the data collection of the 3 different local snow events onto the last graph that had the historic trends. We found that October's event followed the historic trend most closely. December wasn't too bad, and then April had a lot lower density than the temperature trend would show. For the discussion, I'd like to talk about how excited I am about a significant p-value for the daily average temperature compared to the fresh snow density. Very low and highly significant. The original R² value we had was 0.37. We removed some outliers that were pretty outlandish. There was one single night snow event in September of 1945 that was just bananas, and it was recorded of density of like 400 or something, and it really skewed the daily average. And we also removed a couple densities that were recorded at 0, and that's how we ended up with an R² of 0.39 as our end result of density versus average air temperature. And then for our raw data, the October and December events followed more historic averages, and I was very sad when we had our first snow in April and the density was as low as it was, but I was using a different fresh snow sampler than was used in October and December, so that is also something to consider for the change in results there. And then some future research questions that I was considering as I was doing this research. I was considering the different data control, quality control considerations I made. We removed days from history and kind of pretended that they didn't exist if there was no snowfall, which I'm very interested in snowfall, so that made sense for my research, but I'm wondering what trends would look like if we had done it over the course of the entire year and just left spring and summer to remain on the graphs, even though there was no snowfall, just to see what kind of temperature trends follow along there. And I also eliminated some weather variables that might be kind of confounding for the research. I'd be interested in also considering humidity or wind speed to also consider how that would affect snow density. And then last, climate change is a serious crisis that we're going through currently. And as temperatures rise and storm intensity increases, I'm wondering how fresh snow density and water availability is going to be affected. If it's true that temperature increases relate to snow density increases, this could decrease snowpack insulation and cause other adverse effects to ecosystems. And thank you so much for, and I hope you enjoyed my research analysis. I've spent all year doing 100 years worth of snow analysis, and it's been fun. So thank you for listening.
Thank you, Marcee. That was great. I just want to take the opportunity to acknowledge that you were the only undergraduate presenter for Hydrology Days. So big kudos to you. I know that can be a little bit nerve-wracking, and I'm just thrilled that you were able to present. And I also wanted to congratulate you and you know, send my heartfelt sympathies on how your graduation and commencement might be impacted by the current situation, but congratulations nonetheless. And at this point, we can open it up for questions. If anybody has a question, you can raise your hand. I can turn your microphone on, or you can enter them into the chat queue. So we'll just give it a minute or two, see if anything pops up.
Thank you, Sarah.
Yeah.
Hello, Marcee, this is Tim Green. Can you hear me?
I can, thank you.
Great, yeah, thank you for your talk. I just more of a comment, but maybe a question too. Very, very nice to see your data. And, you know, in our models, we have to use kind of generic equations for the snow water equivalent, snow depth relationship. And have had a hard time getting good data sets at this elevation where most of our ag land is. So I think this is very valuable. So I guess how will the data be made available, and are there other sites that you would say are equivalent?
As far as where to download the data?
Well, your particular analyses for the relationships.
I don't have my data published or anything anywhere. So I guess I don't know. I'll have to talk with my mentor, Stephen Fosnot. He's the snow hydrology professor here at CSU.
Yes.
And he will probably be able to help me make my data accessible.
Great. Yeah, that would be great.
Hi, Tim. Thanks for the question. Stephen Fosnot here. Hi, Marcee. Yeah, good job. This, you know, Marcee tried to, you know, take a simple approach so that we can use long-term data sets, you know, using temperature. And we can easily make those data available to you. It's from the Colorado State University Met Station, and you know we'll happily or I'll happily kind of work with you to kind of go through the mechanics of what she's done. She does plan to take all this and put it into a Colorado water paper, so we'll have a more formal version of this. But from the graph that she showed earlier, and Marcee, if you could go back to that plot in your literature review, you can see that.
Do you want this, Stephen?
Yes. Yeah, you can see there's a lot of noise. Those green squares of data that I collected, and one of the issues between kind of the method that I used there and even the data that Marcee and I collected this winter is compared to that 100-year analysis is we were going out and expressly measuring the amount of snow that was on the ground and looking at kind of a shorter time step, whereas with the 100-year analysis, we only have daily data. So there's actually going to be a lot of variability in temperature, and that's why there's a lot of noise in her graphics. But yeah, we'll, as I said, Marcee will write this up, and I'll happily share the specific data that we have, and we can chat offline if anyone else is interested about how we can come up with a better correlation. We have equations for all these curves in this mess here, and so we'll share those as well.
Thank you, Marcee and Steve. Yeah, that's great. I'll touch base with you, Steve. And yeah, as you probably know, we've kind of relied on SNOTEL data, but those are all higher elevation. So that's why I found this interesting.
Yeah, and we have thought about, and this was something that Marcee and I discussed earlier, was looking at the SNOTEL data to see, what densities are you going to get up at those elevations. But we actually, for the amount of snow that falls in Fort Collins and even for smaller snowfall events, you do have a lot of noise in the SNOTEL data. So we have good confidence in the consistency of the data collected at the CSU Met Station, and kudos to Atmospheric Sciences for 40 plus years, Nolan Doskin for really making sure those data are collected.
Yes, agreed. Thank you.
Great, and we did have another question from David. I'm going to try and turn his mic on. I'm not sure if it's enabled on his end. David, are you there? David, does your mic work? Okay, I'll just go ahead and answer. Oh, he said his mic doesn't work. So he's wondering, what are your thoughts on cloud seeding and impacts to the density?
I'm sorry, of what and density?
Cloud seeding.
Cloud seeding. I guess yeah. I don't have any prior knowledge of cloud seeding, so I'm not really sure. Stephen, what do you know about cloud seeding?
So cloud seeding is different methods, historically using silver iodide to add cloud condensation nuclei to get the snow to fall out more. I mean, ultimately, the density of fresh snow is a function of the characteristics of the clouds, the amount of supersaturation and the temperature in which those snow crystals form. So ultimately, if we had a good way of understanding the dynamics within the clouds of what crystals are forming, what the shape is, and then tracking what happens when those crystals from the clouds all the way to the ground, looking at what the temperature is, looking at what the humidity is, etc., then we could get a better idea of what the fresh snow density is. Ivan Dubé with Environment and Climate Change Canada did an analysis about 15 years ago where he used all the layers from a climate model to correlate the fresh snow density with what was happening in the atmosphere. Going back to Tim's question, the reality is we have data on the ground. We don't have those data. So, to try to answer your question, it really depends on what happens with the cloud seeding. If something happens that's, for example, more analogous to snowmaking at ski resorts, that's going to be a lot more dense snow. It really is, it's going to depend more on the conditions within the clouds, in my opinion, than it is to the factor that you're actually seeding the clouds.
Okay, great. Well, I think that's a good segue into our next presenter, which is you, Dr. Fossnot. So I am going to send you screen controls here